morning, good afternoon. I'm not exactly too sure what time it is, but our project is the Visionless Autonomous Quadcopter Landing. I'm Victoria Chen.
I'm Regina, Valencia.
I'm Arvind, Kruthiventy.
I'm Zubin, Kremer, Guha.
I'm Joseph, Arrigo.
So the objective of our project is to autonomously land a quadcopter accurately at a preset location, landing site without the use of computer vision, and as long as the landing site is within a 2-meter radius of the drone. So this is the outline for the rest of our presentation. First, I'm going to be going over a little bit of background. Then we're going to be covering our research, including procedure and results. Then we're going to be going over conclusion, future directions, and finally acknowledgements. So drones are used in many industries in our world today, such as to conduct surveillance. So in the military, drones can be used to take a look at different lands that the military will be crossing. They can also be used in disaster relief efforts in order to check things such as the structural integrity of buildings. Drones can also be used in the transportation of supplies, such as specifically with Amazon's new Amazon Prime Air service. Amazon actually aims to use quadcopters, which is a specific type of drone that I'll be getting into later, in order to transport packages that are under 5 pounds within 30 minutes. Recently, drones have also been increasingly used in the production of photos and videos in order to produce many great movies. And finally, drones have also been used in agriculture in order for precision crop monitoring, which allows farmers to oversee all of their crops and know what areas to target if they need more water or such things like that. And also in order to distribute chemicals such as pesticides as well. And for all of these things that I have listed, quadcopters can specifically be used. So the drone that we specifically chose for our project is the Crazyfly 2.1. And what it is a quadcopter, which is evident from its 4 rotors, which allows it for VTOL. So it is a UAV or an unmanned aerial vehicle, which means it is autonomous and does not need a person to pilot it. And so since it is capable of VTOL, or vertical takeoff and landing, that means that it does not need a landing strip, which would take up a lot of space. And this was key to our project because within GSET, we did not have the space for a landing strip. So its capabilities of being able to take off and land in a single airspace was key. The drone we also chose was Visionless, which means that it does not use computer vision in order to research its surroundings. And this is a benefit to us because with cameras and with vision, cameras are susceptible to either poor or over harsh lighting, which could then distract the drone. And in addition, the processing power that would go toward a camera, without this camera, the processing power could go toward other things such as sensors, which could be ultimately more accurate than a camera.
So the significance of autonomy is that it allows for fully autonomous missions. So with applications such as Amazon's Prime Air, as the services become more widespread, there will be a necessity to make the whole process fully autonomous, including the landing of a drone. The drone has to land precisely and accurately so that the quadcopter itself and its payload is not harmed. When you use a working autonomous landing program, that eliminates the cost of an actual operator and thus makes the drone more commercially viable. So some of the problems that quadcopters actually face is that it relies too heavily on odometry and GPS to determine its position. So odometry is the calculation of its location using its initial velocity and the movement it makes. With sensors that go with odometry, it has a range of error, and as it moves too far, that can compound along with the quadcopter drifting in certain directions. Along with the GPS range of error of 2 meters, this can create a sense of uncertainty as to where the quadcopter actually is. So the landing site that we used for this experiment has 4 vinyl pipes arranged in a square formation. We actually tested 2 other materials instead of the pipes, which were wooden dowels and PVC pipes. We actually found that the vinyl pipes worked the best with the distance sensors on the quadcopter and that it had the most surface area. To add more height to those markers, we had balsa wood, and on the floor we had plywood so that the drone can land on top of it. To make the structure more cohesive and to ensure that the drone sensors would actually sense the structure, we spray painted it one color.
So for the purpose of our project, we assume that GPS is able to get the drone within around 2 meters radius of the landing site, but it doesn't know anything more than that. So to find the landing site, it actually has to use the 4 distance sensors that it has on it, which use infrared lasers that reflect off the landing site. Then it detects the landing markers, which we showed before, which are in a square formation, specifically because it is very simple and more or less the same from all angles that the drone can see. So for the first stage, the drone will just lift off from where it is and turn around to best try and see whether there's anything in the general vicinity. So that would be the stage right over here. And if it sees an object, it will start to approach it, but if it doesn't, it has to move on to the next stage of our algorithm, which is the circle search. In circle search, it moves in concentric circles of increasing radius while still detecting, which actually allows it to overlap or have pretty much no overlap with its search, which is the most efficient, which is especially important because of our limited battery life. The same deal here. If it sees something, it's going to approach it, and if it doesn't, it's going to continue to go in the larger and larger circles until it's completed 3, which is more or less the range. And if it doesn't see them in 3, it'll have one last ditch attempt to try and go fully to the 2-meter radius and do one last circle. And if it doesn't find it, then something definitely went wrong and can't land. So once it's found one of the markers, it needs to find another, and after that actually another, because 3 points are necessary for actually locating yourself in 2D space. So to do this, the drone is going to come up to one of the markers and start circling around it until it sees another one of the markers with its another sensor. It's then going to move halfway between them and move halfway between that distance to the center. However, that's still only 2 markers, so the drone could either be here or here from its perspective. So after that, it needs to move forward until it sees these to determine that it's on the right side. And if it doesn't see them, it knows that the landing site should actually be over here, and it'll move all the way back over here. Oh, and now we have a video of it working. Okay, so now it's lifting off and starting the turn function. Completed 1 turn, so now it's starting the circle search. And on the first lap, it actually didn't see that marker, so it's going to do another larger circle. Now one of the side sensors sees the marker, so it turns around that one, finds the second marker, moves forward to check for the other 2, and since it finds them, it moves backward and lands in the center.
So when it came time to collect data, we decided that it would be best to collect it in 2 different stages. In the first stage, for every trial, we placed a quadcopter down 90 centimeters away from the center on the same position every time. We did this to ensure that it would work in that fixed circumstance before we started doing it from random locations. And if we received errors in those random locations, we wouldn't know what happened. So when we placed it down and when we tested it about 20 times, this is the graph of everywhere it landed. The four circles represent the poles of the landing space, and the blue dots represent each of the landing points. You can see that from where it landed, it generally stuck towards the top half of the landing pad here, and that's due to a source of error, one of 3 sources of error that we'll talk about later. And numerically, it had a mean average distance from the center of about 22 centimeters and a standard deviation of about 14, and that means that the 0 point, the center, is with just under 2 standard deviations away from the mean, showing that there's a higher percentage chance of it happening. And that's proven by our statistics that we measured. 52% of the time, the quadcopter did land on the landing pad, and 16% it landed within 10 centimeters of the center. Now, for our second set of trials, we thought we could improve upon that, so we made some minor changes to the algorithm to allow for smoother flight and more accurate flight, and you can see generally that it worked. There's a more precision towards the center of the landing pad here. You can see there's far fewer landing sites off of the landing pad, and it's generally focused around the center. Numerically, there was a mean of about 14 centimeters from the center every time, and a standard deviation of 12.5 centimeters. And since the distance between the mean and standard deviation compressed, that means that there's an even higher percentage from last time of it actually landing in the center. And that's, again, supported by our statistical data. 83% of the time, it would land on the landing pad, and 34% of the time, it landed within 10 centimeters of the center, which is about 20 to 30% increases from the first set of testing.
So these are some of the challenges that we faced over the course of the project, and the first three were inherent to how the drone's constructed. The first one was the fragility of the propellers, and this was because the drone is of a small scale, so its propellers are made out of thin ABS plastic, and this wasn't much of an issue at the beginning of the project because we had plenty of spares to account for any of the crashes, but when we started running full flight tests, it started becoming a more important issue, and during week 3, we ended up running out of all the spares that we had. So for all week 3, we didn't have any way to directly test the changes that we made to the algorithm, and to account for this, we actually bought several sets of propellers afterwards, both clockwise and counterclockwise, to account for any future crashes. And then the second and third issues are mainly because batteries, okay, so quadcopters are limited to a certain amount of battery mass that they can carry before the thrust they produce can't actually carry the battery mass that they have on board. So smaller batteries on drones end up meaning that you have less flight time, and our flight time was limited to 7 minutes, but a 45-minute charging period. So you can imagine that we would only be able to run a few flight tests before we ran out of battery and ended up having to charge. So the way we countered that was we brought several batteries, and then after they arrived, we would change them out for the batteries on the drone that actually went through flight tests, and then run flight tests continuously. The third issue is, again, ground effect. Ground effect is something where the airflow over the propellers ends up deflecting off the ground, and this makes the propeller rise up very quickly. But because it rises up at a rapid pace, it can't maintain its stability, and it moves away from where it started. And this was not an issue during the beginning process because our algorithm was only running parts of what it was supposed to do. But during flight tests, it started moving away from where it started, and this meant that it was a major source of error during the later part of the project. So the main issue right now that's preventing us from complete accuracy is drift. So occasionally the flight controller can't compensate for the motors being overpowered on one side compared to the other side. So the drone eventually moves in one of the 4 directions. And currently we're only able to compensate for it by accounting for how the drone moves in 3D space. And we can basically give the drone extra time to travel a certain distance or add restrictions to make sure that it's within the parameters that it needs to be. So we made corrections to complete the full circle. And this was a major issue during the beginning part of the process because the circular path that the drone was supposed to move in ended up turning into an ellipse, and that meant that it would take more time to complete the circle than we originally planned. So we added factors to compensate for that by increasing the amount of time that the drone has by 14%. And then we made corrections to initiate the circle. And this is really important because when you're making a lot of fine movements in space, you need to approach and circle the obstacles that you detect correctly so that you can move towards the center. So we had to fine tune the angle that the drone started in to make sure that there's not a major source of error that ended up causing the drone to not land on the center. And then there's distance drift, and this continues to be an issue because there's no real way to solve this since smaller drones are always prone to drifting in a certain direction, since any small disturbance can move them away from their position. But we ended up compensating for it by reducing the speed that they move at towards certain obstacles so that it would correctly approach and detect the other markers. The last one is the drone's again fragile, but now as we run full flight tests, if it ends up crashing, it disconnects the sensors that are responsible for orienting itself in 3D space, and this was a major issue, but this won't be a major issue when it comes to larger drones that have a more robust build, and they're less moved by drift or other environmental conditions. So our algorithm currently is able to achieve an accuracy of within 10 centimeters of the landing site, and this might sound large compared to the landing site itself, but if you consider that the drone is about like 4 centimeters of a wheelbase, this means that small disruptions can actually move it very far from the landing site, and our compensation factors actually achieved a reasonable accuracy. But if we have larger drones, it's very easy to reduce the distance from the landing site center, and that's what we plan to do in the future because this algorithm requires more optimization so it can deal with larger search areas and the amount of time it takes to find the landing site. So the application for these algorithms is basically when you have to navigate in a tight space, you have to make a lot of fine movements, and GPS sensors don't really have the accuracy to do that because consumer-grade GPS sensors can only achieve an accuracy of between 2 to 7.8 meters. And if you're moving in a tight space, you might not even have that distance available to you. So you need to use either odometry or sensor-based navigation. And as we said before, odometry has severe error associated with it because if you start with an error at the beginning, you end up compounding that error over the amount of movements that you make. And eventually you'll be extremely far from the location that you started or wanted. So it's very important to use sensor-based navigation to correct yourself when these deviations happen. And that's where this drone will be applicable for. And it will allow drones in real-life scenarios where you have to move around obstacles such as trees within a tight space to make these movements and orient itself in 3D space. And again, because we used a very low-budget drone to accomplish this, this is almost universal in its applicability, and that means that it can be used for drones that are both of lower cost but higher cost as well. The future directions that we want to take this drone in is we want to optimize it so it runs for a larger search area, and that means that in a real life scenario, you might not be within 2 meters of the landing site. You might be within 5 or 7.8 meters, and that means that this algorithm would take a significantly longer amount of time to detect a landing site. So we want to optimize it to deal with these larger areas, and we also want to optimize it for cases where there's other obstacles that the drone currently thinks is a landing marker, but is not. So we want to deal with these false positives, as well as increase the stability by adding something called PID. And PID is basically just a feedback control loop. So what it does is it keeps correcting for the error in the drone's movement until it follows the straight path or the path that it's supposed to follow in the space.
So these are the people that we like to acknowledge and thank. Brian Lai, Helen Sages, Michael Higgins, Shravan Venkatesan, Dean Antoine, the director of GSET, Rutgers University, Rutgers School of Engineering, Lockheed Martin, the state of New Jersey Governor's School alumni, and the New Jersey Space Grant Consortium for their generous sponsorship and support of this project and program.
For search quadcopter, like running this algorithm, it's very computationally efficient. So as you saw before, it seems very simple, and that means that it's able to work with a lot of hardware. So maybe if you can program a $30 drone, it would also accomplish the same task that our drone did too, if it has the proper sensors.
Question for the second set of experiments you did. You mentioned that for the first set you used a fixed starting point, and you mentioned you use a random starting point in the second. Can you say a little bit more about it? What is random? Was it entire space? Was it outside the landing zone?
For the random starting point, we used a random number generator to generate random X and Y coordinates within a 2-meter radius around the center. Just a random, we generated randomly online, just any numbers.
Could have been that you actually start in the landing position.
Yes.
And it will work within the landing site too. Okay.
Just a quick question, I missed. What were you using for your sensors?
We were using infrared laser ranging sensors.
Thank you.
Just a quick question. So, what was it like programming the drone, and what challenges did you have? And like, did you use computers for it, or was it like all based on the sensors?
So we had a lot of difficulties with programming the drone because drones, again, because it's a small drone, it's very sensitive. And during the beginning stages of our testing, we would end up with a lot of crashes. And even a small error can throw off the code and result in an exception. So we would end up with a bunch of failed tests, recharging the batteries, and then going back. So it was very difficult to work with the drone. And the drone has a steep learning curve. So the drone comes with its own library, like the code that it should follow commands from, and that library is very difficult to use for beginners if you don't already have experience.